The Ed Gray Power System. The power tube presented to the public by Edwin Gray SNR operates by generating a series of very short, very sharp pulses using a spark gap. This device is reputed to have a power output which is 100 times that of the power input. Ed Gray and his electric pulse motor are very famous, but as far as I am aware, nobody has successfully replicated this claimed performance. Further, an in-depth examination of the background details by Mr. Mark McKay have turned up a number of facts which present a very different picture, and while it is perfectly correct to say that spark gap pulses generate a good waveform for shocking the local zero-point energy field into the sort of imbalance which can provide a massive power inflow into a device or circuit, we need to be careful to get the full facts in this case. First, let us put the whole thing in its proper perspective. In May 1973, Caltech in the US performed an independent assessment of an engine provided to them by Edwin Gray. They measured the input and the output and certified that the output power was 275 greater than the input power. This demonstrates clearly that excess power can be drawn into an engine and provide a performance which can power both the engine as well as doing additional useful work. Having said that, it needs to be made clear that Edwin Gray did not build that small motor, did not understand how it worked, nor did he ever disclose the design in any of the patents which he obtained afterwards. We need to follow the sequence of events and notice when each thing happened. The history is as follows. In 1957, a Russian immigrant to the USA, one Alexei Popov, showed Edwin Gray a circuit which he said that he had been shown by Nikola Tesla. Edwin Gray did not understand the circuit and had no idea how to create anything useful based on it. He then joined up with his next-door neighbor Marvin Cole, who held a master's degree in mechanical engineering and who, unlike Gray, was able to understand the circuitry. In 1958, Ed Gray, shown above, left the Los Angeles area in a hurry. From 1958 to 1967 Marvin Cole, working alone, designed and built ever more powerful prototype engines, and it was a small one of these which was tested by Caltech. In this period, Marvin also developed ever more powerful power supplies, which are the really important item in all of this. In 1967, Ed Gray rejoins Marvin Cole and together from 1967 to 1972 they solicited venture capital and promoted the technology. Early in 1972, Marvin Cole disappeared and never saw Gray again. It is not clear if he was intimidated, died, or just did not want to be involved in all the publicity and effort needed to turn the prototype engines into a commercial product. No matter what the reason, the result was that Edwin Gray was suddenly disconnected from the brains behind the project, and that left him in a very difficult position. He didn't want to let go of the dream of becoming rich through this spectacular development, and so he tried to continue the development on his own. As already mentioned, in May of the following year, 1973, Gray had a small Marvin Cole motor independently third-party tested at the famous Caltech laboratory in Los Angeles, where a measured input of just 27 watts produced a measured output of 10 horsepower, 7460 watts. The objective was to provide solid evidence of a new technology which was capable of changing the world and so would attract investors. To further boost his image and convince potential investors, in that same year of 1973, Edwin staged demonstrations which jumped electromagnets up into the air, showing the strength of the power which drove the Marvin Cole engines. It is very important to understand that all of Edwin Gray's patents were applied for after the departure of Marvin Cole. These do not disclose the technology tested by Caltech, and it must be understood that Edwin was very much afraid of revealing anything important in any of the patents in case some other person would understand the things which were a mystery to him and snatch away the prize of commercial success. So, please be aware that the patents were applied for solely to encourage investors and most definitely not to show any significant details. Edwin then assembled a small team of people to attempt to understand and advance the work of Marvin Cole. However, the subsequent changes to the Cole implementations did not result in genuine, reliable working motors due to Gray's lack of understanding of the underlying energy tapping methods used by Cole. The power tube shown in Gray's patents has never been shown to provide the COP equal 100 energy performance which is sometimes mentioned, nor did it form part of Marvin Cole's system. In 1976, Edwin Gray shows 3 of these power tubes driving one, failed version, motor. This technique is in direct conflict with Marvin Cole's successful technique which had 24 separate power supplies driving the motor. Please understand that the power gathering mechanism of the Cole system is the key feature of all of the successful systems. Unfortunately, as far as I am aware, that technology has never been disclosed. Just to clarify the differences, let me briefly outline my understanding of what Edwin Gray put forward as the power gathering system of the motors which he attempted to develop after he parted company with Marvin Cole. Edwin shows 3 power tubes connected to the engine like this. Here, 3 separate sets of electromagnets inside the motor are pulsed in sequence by 3 separate identical circuits, each driving the electromagnets via a power tube. Marvin Cole's system used 24 separate power gathering circuits which drove 24 separate electromagnets inside the motor. Power tubes were not used. You may wish to try Edwin's power tube for yourself, so let me explain the basic details as I understand them. The overall circuit is like this. You will notice that the power driving the load does not come from the battery as the battery circuit produces the spark inside the power tube and nothing else. The motor's electromagnet winding is driven by power picked up by the copper shells around a 1/2 inch, 12 mm, diameter, copper rod, spark gap electrode which has silver-coated tips. The circuit supposedly operates as follows. The driving 12V battery B1, continuously powers an oscillator which uses transformer T to step the voltage up to a high level. This high voltage is full wave rectified by a bridge of high voltage diodes, and the resulting DC voltage is fed to capacitor C. If any malfunction causes this DC voltage to get too high for safety, the discharge contacts D cause the voltage to discharge via a spark to the earth connection. Under normal circumstances, the high voltage on C creates a spark in the power tube P when its circuit is completed by the closing of switch A, which is used to synchronize the power pulse to the rotation position of the electric motor's shaft. The switch drives a monostable circuit which delivers a very short enabling pulse to V, the one-way current switch, which is a powerful electronic triode valve. These days, it is very difficult to get a valve of that type, and the best source is probably the power output valve from a World War II radio transmitter. The power tube P has a resistor shown in it. This was actually a block of carbon, and as such, will have had minimal electrical resistance. However, several different devices which appear to have COP1 power outputs use a spark gap associated with a carbon electrode, so there may well be a second effect coming into play here. A key factor in this circuit is the fact that the power which drives the motor does not come from this electrical circuit at all, but from the apparently disconnected cylinders inside power tube P. This power is cold electricity, flowing into the circuit from the local environment. Remember that Floyd Sweet in his first measured test had an 500 watt electrical output from a power input of just 0.31 of a milliwatt. In this circuit, the motor represents just one of the coil windings inside the electric motor, and instead of the power flowing through the motor being fed to ground as normal, it is fed to the plus 12 volts of battery B2. The objective was to charge battery B2, the charging current being limited by capacitor C2, the idea being that B1 and B2 could be swapped over when B1 became discharged. This arrangement was soon discontinued, and battery B2 was charged from a standard car alternator driven by the engine in an entirely conventional manner. A rapid and abrupt electrical discharge is produced by generating a spark, and power pickup is achieved by 2 copper cylinders surrounding the conductor which carries the spark current. There is more than one way of doing this. In the following diagram, the spark gap is shown exposed to make it easier to see, but in practice, the perforated copper shells extend to cover the spark gap. A full and detailed description of how it is believed that Ed Gray's system works is given in Peter Lindemann's book The Free Energy Secrets of Cold Electricity, which is available via the website http://www.freeenergy.ws/products.html. Tesla used this spark gap method with spark quenching provided by a strong magnetic field at right angles to the spark, in order to get really high-quality DC pulses with durations of 1 microsecond or less. Pulse trains of individual pulses with very short durations produce heat, spontaneous lighting, cooling, etc. depending on the frequency of the pulsing. The power tube is placed around a heavy-duty copper conductor which is pulsed, unbalancing the zero-point energy field, and a tiny part of the resulting energy flow as the field moves back into equilibrium again, is captured by the surrounding perforated copper shells. While the switching valve in the electronics circuit looks like a very difficult component to come by, the possibility of constructing one yourself should be considered. Essentially, a thermionic valve is a simple device. A heated filament at one end of the tube emits electrons. A high voltage along the length of the tube provides an electrical urge for those electrons to flow along the tube. A metal grid between the heated filament and the electrode at the far end of the tube can be used to prevent that current flow by connecting an opposing voltage to that grid. It is that grid voltage which is turned off very briefly to provide the current pulse to one set of motor windings. A seeming obstacle is producing the glass envelope for the valve, but there is actually no need for the valve to have a glass container, and a wide range of other materials can be used. Another obstacle is creating a vacuum inside the valve housing, but it has been stated that the main reason why these valves have a vacuum inside them was mainly commercial, namely, an attempt to encourage people not to make their own. It is said that there is no reason why a thermionic valve should not have air inside it. The current flow is not a spark. I have no idea how accurate, or inaccurate, this information on valve construction is, but I strongly suspect that it is correct. Marvin Cole's power system produced cold electricity which could power lights and other devices. It was frequently demonstrated that the output was not conventional electricity and powered light bulbs which were placed under water, and at the same time, it was quite safe for a hand to be put into that same water along with the lit bulb. The glass of the conventional bulbs used in these demonstrations would have shattered when placed under water if they had been powered by conventional hot electricity, as the sudden change in temperature would have broken the glass. Powered as they were by cold electricity, they ran cool, and so there was no stress on the glass when submerged in water. The construction of the pickup tube is not particularly difficult. It is comprised of a Teflon, plastic, cylinder of about 80 mm diameter with Teflon plates at each end, grooved to hold the pickup cylinders in place. A pair of 12 mm diameter copper rods are positioned down the center of the cylinder and provided with a means to adjust the gap between them where they meet. The rod ends form the spark gap, and these ends are plated with silver. One rod has a graphite block inserted in it, using a push-fit connection into slots cut in the bar. This carbon insert is supposedly a resistor, but in fact it is an important part of the excess energy generation system. In some successful constructions of the tube, an 8-inch long, half-inch diameter carbon rod with a silver tip is used for one of the electrodes. The 2 or 3 cylinder shells which pick up the radiant energy are constructed from copper sheet. The gap between the outside of one cylinder and the inside of the surrounding cylinder is about 6 mm. These cylinders are more effective if they have a matrix of holes drilled in them. They are connected together electrically, and the connection is led out through the Teflon casing to feed the load circuit. The cylinder contains air rather than a vacuum or an inert gas. The copper cylinders are held in place by push-fit supports, one set positioned between the outside of the smaller cylinder and the inside of the larger cylinder. The second set are placed between the outside of the larger cylinder and the inside of the housing tube. The power tube is constructed this way because the radiant energy wave generated by the sharp pulse of current through the electrodes radiates out at right angles to the electrodes. Peter Lindemann points out that Ed Gray's power conversion tube circuit is effectively a copy of Nikola Tesla's circuit for doing the same thing. This was disclosed by Tesla in his Philadelphia and St. Louis lecture in 1893 and shows how loads can be powered when a high voltage source is pulsed by a magnetically quenched sparks. This creates DC pulses of very short duration. The diagram above illustrates the difference between the magnetic field generated around a conductor fed with a pulse of direct current and the radiant energy waves created by that pulse. If a sharp current pulse is driven down a vertical wire, it causes two different types of field. The first field is magnetic, where the lines of magnetic force rotate around the wire. These lines are horizontal, and rotate clockwise when viewed from above. The magnetic field remains as long as the current flows down the wire. The second field is the radiant energy wave. This wave will only occur if the current pulse is in one direction, i.e. it will not occur if the wire is fed with alternating current. The wave radiates out horizontally from the vertical wire in every direction in the form of a shock wave. It is a one-off event and does not repeat if the current in the wire is maintained. The radiant energy briefly unbalances the zero-point energy field, and that causes an energy flow as the field moves back into equilibrium again. The radiant energy wave is not restricted to a single plane as shown in the diagram above, which is intended to indicate the difference between the electromagnetic field circling around the wire, and the radiant energy field which radiates away from the wire. Both of these fields occur at all points along the full length of the wire as shown here. Radiant energy, when converted to electrical power, produces a different kind of electrical power to that produced by batteries and by the main supply. Power a motor with conventional electricity and it gets hot under load. Power the same motor by radiant energy electricity and under load the motor gets cold. Really overload it by stalling it and the motor housing is likely to be covered with frost. That is why this form of electricity is referred to as cold electricity. In his book Cold War Secrets, HAARP and Beyond, Gary Vasilatos quotes research work done in this area by Tesla and others. Tesla's experiments. In 1889 Tesla began experimenting with capacitors charged to high voltages and discharged in very short time intervals. These very short pulses produced very sharp shock waves which he felt across the front of his whole body. He was aware that closing a switch on a high voltage dynamo often produced a stinging shock. This was believed to be static electricity and it occurred only at switch on and only for a few milliseconds. However, in those few milliseconds, bluish needles of energy stand out from the electrical cables and they leak to ground, often through the bodies of any people standing nearby, causing immediate death if the installation is large. While the generators of that time were rated at some thousands of volts, these discharges were millions of volts in intensity. The generator problem was eliminated by the use of highly insulated switches which were provided with a very large ground connection. Tesla was intrigued by this phenomenon which appeared to match the effect of his capacitor discharges. He calculated that the voltages produced were hundreds of times greater than could be supplied by the capacitor or generator. It was clear that the power supplied was being amplified or augmented in some way, but the question was, from where was the extra energy coming? Tesla continued to investigate through experiments, taking precautions against the high voltages being produced. He was soon able to produce these shock waves whenever he wanted to. The shock waves produced a stinging sensation no matter where he stood in his laboratory, and hands and face were particularly sensitive to the wave. These waves radiated out and penetrated metal, glass and every other kind of material. This was clearly not an electromagnetic wave, so he called the new wave radiant electricity. Tesla searched the literature to find references to this radiant energy but he could not find much. In 1842, Dr. Joseph Henry had observed that steel needles were magnetized by a Leyden jar spark discharge located on a different floor of the building. The magnetizing wave had passed through brick walls, oak doors, heavy stone and iron flooring and tin ceilings to reach the needles located in a vault in the cellar. In 1872, Elihu Thomson took a large Ruhmkorff spark coil, attached one pole of the coil to a cold water pipe and the other pole to a metal tabletop. This resulted in a series of massive sparks which electrified the metal door knob of the room and produced the stinging shock waves which Tesla was investigating. He found that any insulated metal object anywhere in the building would produce long continuous white sparks discharging to ground. This discovery was written up briefly in the Scientific American Journal later that year. Tesla concluded that all of the phenomena which he had observed implied the presence of a medium of gaseous structure, that is, one consisting of independent carriers capable of free motion. Besides the air, another medium is present. This invisible medium is capable of carrying waves of energy through all substances, which suggests that, if physical, its basic structure is much smaller than the atoms which make up commonplace materials, allowing the stream of matter to pass freely through all solids. It appears that all of space is filled with this matter. Thomas Henry Moray demonstrated this energy flow passing through glass and lighting standard electric light bulbs. Harold Aspdin performed an experiment known as the Aspdin effect, which also indicates the presence of this medium. Harold made this discovery when running tests not related to the subject. He started an electric motor which had a rotor mass of 800 grams and recorded the fact that it took an energy input of 300 joules to bring it up to its running speed of 3,250 revolutions per minute when it was driving no load. The rotor having a mass of 800 grams and spinning at that speed, its kinetic energy together with that of the drive motor is no more than 15 joules, contrasting with the excessive energy of 300 joules needed to get it rotating at that speed. If the motor is left running for 5 minutes or more, and then switched off, it comes to rest after a few seconds. But, the motor can then be started again, in the same or opposite direction, and brought up to speed with only 30 joules provided that the time lapse between stopping and restarting is no more than a minute or so. If there is a delay of several minutes, then an energy input of 300 joules is needed to get the rotor spinning again. This is not a transient heating phenomenon. At all times the bearing housings feel cool, and any heating in the drive motor would imply an increase of resistance and a build-up of power to a higher steady-state condition. The experimental evidence is that there is something unseen, which is put into motion by the machine rotor. That something has an effective mass density 20 times that of the rotor, but it is something that can move independently and take several minutes to decay, while the motor comes to rest in a few seconds. Two machines of different rotor size and composition reveal the phenomenon, and tests indicate variations with time of day and compass orientation of the spin axis. One machine, the one incorporating weaker magnets, showed evidence of gaining strength magnetically during the tests, which were repeated over a period of several days. This clearly shows that there is an unseen medium which interacts with everyday objects and actions, and confirms Tesla's discovery. Tesla continued to experiment and determined that a very short unidirectional pulse is necessary to generate the radiant energy wave. In other words, an alternating voltage does not create the effect, it has to be a DC pulse. The shorter the pulse time and the higher the voltage, the greater the energy wave. He found that using a capacitor and an arc discharge mechanism with a very powerful permanent magnet placed at right angles to the spark, improved the performance of his equipment by a major factor. Additional experiments showed that the effects were altered by adjusting the duration of the electrical pulse. In each instance, the power of the radiated energy appeared to be constant irrespective of the distance from his apparatus. The energy was in the form of individual longitudinal waves. Objects placed near the equipment became powerfully electrified, retaining their charge for many minutes after the equipment was switched off. Tesla was using a charging dynamo as a power source, and he found that if he moved his magnetic discharger to one side of the dynamo, the radiant wave was positive. If he moved the magnetic discharger towards the other side of the dynamo, the radiant wave became negative in sign. This was clearly a new electrical force which traveled as light-like rays, showing them to be different in nature to the electromagnetic waves of Maxwell. Investigating the effects of adjusting the duration of the pulses, Tesla found that a pulse train which had individual pulses with durations exceeding 100 microseconds, produced pain and mechanical pressures. At this duration, Objects in the field visibly vibrated and were even pushed along by the field. Thin wires subjected to sudden bursts of the radiant field, exploded into vapor. When the pulse duration was reduced to 100 microseconds or below, the painful effect was no longer felt and the waves are harmless. With a pulse duration of 1 microsecond, strong physiological heat was felt. With even shorter pulse durations, spontaneous illuminations capable of filling rooms with white light were produced. Even shorter pulses produced cool room-penetrating breezes with an accompanying uplift in mood and awareness. These effects have been verified by Eric Dollard, who has written about them in some detail. In 1890, Tesla discovered that if he placed a 2-foot-long single-turn deep copper helix coil near his magnetic disruptor, the thin-walled coil developed a sheath of white sparks with long silvery white streamers rising from the top of the coil. These discharges appeared to have much higher voltages than the generating circuit. This effect was greatly increased if the coil was placed inside the disruptor wire circle. The discharge seemed to hug the surface of the coil with a strange affinity, and rode up its surface to the open end. The shock wave flowed over the coil at right angles to the windings and produced very long discharges from the top of the coil. With the disruptor charge jumping 1 inch in its magnetic housing, the coil streamers were more than 2 feet in length. This effect was generated at the moment when the magnetic field quenched the spark, and it was wholly unknown at that time. This train of very short unidirectional pulses causes a very strange field to expand outwards. This field resembles a stuttering electrostatic field but has a far more powerful effect than would be expected from an electrostatic charge. Tesla was unable to account for the enormous voltage multiplication of his apparatus using any of the electrical formula of his day. He therefore presumed that the effect was entirely due to radiant transformation rules, which would have to be determined through experimental measurements. This he proceeded to do. Tesla had discovered a new induction law where radiant shock waves actually auto-intensified when encountering segmented objects. The segmentation was the key to releasing the action. Radiant shock waves encountered a helix and flashed over the outer skin, from end to end. This shock wave did not pass through the windings of the coil but treated the surface of the coil as a transmission path. Measurements showed that the voltage increase along the surface of the coil was exactly proportional to the length traveled along the coil, with the voltage increase reaching values of 10,000 volts per inch of coil. The 10,000 volts which he was feeding to his 24-inch coil were being magnified to 240,000 volts at the end of his coil. This was unheard of for simple equipment like that. Tesla also discovered that the voltage increase was mathematically linked to the resistance of the coil winding, with higher resistance windings producing higher voltages. Tesla then began to refer to his disruptor loop as his special primary and to the long helical coil as his special secondary, but he never intended anyone to equate these terms to those referring to electromagnetic transformers, which operate in a completely different way. There was an attribute which baffled Tesla for a time. His measurements showed that there was no current flowing in the long copper secondary coil. Voltage was rising with every inch of the coil, but there was no current flow in the coil itself. Tesla started to refer to his measured results as his electrostatic induction laws. He found that each coil had its own optimum pulse duration and that the circuit driving it needed to be tuned to the coil by adjusting the length of the pulses to give the best performance. Tesla then noticed that the results given by his experiments paralleled the equations for dynamic gas movements, so he began wondering if the white flame discharges might not be a gaseous manifestation of electrostatic force. He found that when a metal point was connected to the upper terminal of the secondary coil, the streamers were directed very much like water flowing through a pipe. When the stream was directed at distant metal plates, it produced electronic charges which could be measured as current at the receiving site, but in transit, no current existed. The current only appeared when the stream was intercepted. Eric Dollard has stated that this intercepted current can reach several hundred or even thousands of amps. Tesla made another remarkable discovery. He connected a very heavy U-shaped copper bar directly across the primary of his disruptor, forming a dead short circuit. He then connected several ordinary incandescent filament bulbs between the legs of the U-shaped bar. When the equipment was powered up, the lamps lit with a brilliant cold white light. This is quite impossible with conventional electricity, and it shows clearly that what Tesla was dealing with was something new. This new energy is sometimes called cold electricity, and Edwin Gray Sr. demonstrated how different it is by lighting incandescent filament bulbs directly from his power tube, submerging them in water and putting his hand in the water. Cold electricity is generally considered to be harmless to humans. Ed Gray's power tube operates by generating radiant electricity waves by using a spark gap, and collecting the energy using 3 encasing copper cylinders surrounding the spark gap. The cylinders are drilled with many holes as that enhances the pickup, and the load is driven directly from the current in the cylinders. When lighting bulbs, Ed used an air cord transformer made of just a few turns of very heavy wire. I, personally, am aware of 2 people who have independently reproduced Ed's power tube. Tesla viewed the streamers coming off his coils as being wasted energy, so he tried to suppress them. He tried a conical coil but found that this accentuated the problem. He then tried placing a copper sphere at the top of his coil. This stopped the streamers, but electrons were dislodged from the copper sphere, creating really dangerous conditions. This implied that metals generate electron flows when struck by the coil streamers, as had been seen when the streamers had been aimed at remote metal plates and current was generated as a result. Tesla designed, built and used large globe lamps which required only a single external plate for receiving the radiant energy. No matter how far away these lamps were from the radiant source, they became brilliantly lit, almost to the level of an arc lamp, and far, far brighter than any of the conventional Edison filament lamps. By adjusting the voltage and the pulse duration of his apparatus, Tesla could also heat or cool a room. The Tesla switch. Nikola Tesla introduced the world to alternating current, AC, but later on he moved from AC to very short, sharp pulses of direct current, DC. He found that by adjusting the frequency and duration of these high voltage pulses, that he could produce a whole range of effects drawn from the environment, heating, cooling, lighting, etc. The important point to note is that the pulses were drawing energy directly from the immediate environment. Leaving aside the advanced equipment which Tesla was using during those experiments and moving to Tesla's simple-looking 4-battery switch, we discover the same background operation of sharp voltage pulses drawing free energy from the environment. Consider the Electrodyne Corp circuit, the Manual of Free Energy Devices and Systems, 1986, Vol. 1, tested by them for a period of 3 years. This simple-looking circuit needs to have an inductive load, preferably a motor, but that aside, consider the results of that very extended period of testing. If the switching rate and switching quality were of a sufficiently high standard, then the load could be powered indefinitely. The batteries used were ordinary lead-acid batteries, and after the 3 years of tests, the batteries appeared to be in perfect condition. Their tests revealed a number of very interesting things. If the circuit was switched off and the batteries discharged to a low level, then when the circuit was switched on again, the batteries returned to full charge in under 1 minute. As no electrical charging circuit was connected to the system, the energy which charged those batteries had to be flowing into the batteries, and load, from outside the circuit. The similarity with the Bedini pulsed battery charger circuits immediately springs to mind, especially as no heating occurred in the batteries in spite of the massive charging rate. If the circuit was switched off and heavy current drawn from the batteries, then heat would be produced, which is quite normal for battery discharging. The system operated lights, heaters, television sets, small motors and a 30 horsepower electric motor. If left undisturbed, with the circuit running, then each battery would charge up to nearly 36 volts with no apparent ill effects. Control circuitry was developed to prevent this overcharging. Here we have spectacular battery charging and performance, quite outside the normal range associated with these ordinary lead-acid batteries. Are they being fed very short, very sharp pulses, like the previous 2 systems? It would look as if they were not, but one other very interesting piece of information coming from Electrodyne is that the circuit would not operate correctly if the switching rate was less than 100 Hz, that is 100 switchings in 1 second. The Electrodyne switching was done mechanically via 3 discs mounted on the shaft of a small motor. It is distinctly possible that the brushes pressing on those rotating discs experienced the equivalent of switch bounce which plagues mechanical switches used with electronic circuits. Instead of a single, clean changeover from off to on states, there is a series of very short makes and breaks of the circuit. If this happened with the Electrodyne mechanical switching, then the circuit would have experienced very short, sharp electrical pulses at the instant of switching. The fact that the switching speed had to reach 100 per second before the effect started happening is certainly interesting, though not proof by any means. One other detail reported by the Electrodyne testers, is that if the switching speed exceeded 800 times per second, that it was dangerous, but unfortunately, they didn't say why or how it was dangerous. It clearly was not a major problem with the batteries as they were reported to be in good shape after 3 years of testing, so definitely no exploding batteries there. It could well be as simple a thing that the voltage on each battery rose so high that it exceeded the voltage specifications of the circuit components, or the loads being powered, which is a distinct possibility. In my opinion, considering the way that the batteries responded, it would be perfectly reasonable to take it that short pulses were being generated by their mechanical system. If that is the case, then here is another system drawing Phi energy from the environment via sharp voltage pulses. The Tesla switch circuit has some very interesting features. Pupils in school are taught that if a bulb is connected across a battery, a current flows from the battery, through the bulb and back to the battery. This current causes the bulb to light, and after a time, the battery runs down and is no longer able to light the bulb. This is completely correct. However, this teaching gives the wrong impression. It implies that the work done in lighting the bulb uses up the electricity coming from the battery and that the battery somehow has a store of electricity, something like the sand in an hourglass or egg timer, which when it runs out will no longer be able to light the bulb. In passing, it can be remarked that not a single electron which flows at a power station actually comes out of your mains wall socket. The reality is that the power station electrons flow in one winding of your local step-down transformer and cause a fluctuating magnetic field there which causes some of the many free electrons in your locality to flow into another winding of the transformer and then onto your wall socket. If you were to cause those same magnetic fluctuations yourself, then you would receive the same level of electrical power without the power company being involved. Interestingly, those same school teachers will show the correct picture of the circuit, drawing it like this. You will notice that the 1 amp current flowing out of the bulb is exactly the same as the 1 amp current flowing into the bulb. Exactly the same amount of current comes out of the bulb as the current which flows into the bulb. So, how much current is used up in doing the work of lighting the bulb? Answer: none. Energy is never destroyed. The most that can happen to it is that it gets converted from one form to another. So why does the battery end up not being able to light the bulb anymore? Well, that is a feature of the way that batteries operate. If the current flow is in one direction, then the battery gets charged up, and if it is in the other direction, then the battery gets discharged. The battery getting run down has nothing to do with the current flowing through the bulb. The battery would get run down if the bulb were left out of the circuit. The useful work of creating light by having the current flow through the bulb does not use up any current, and more importantly, it does not use up any energy. Energy cannot be used up, it just gets transformed from one form to another. This is difficult to understand as we have been taught that we have to keep buying energy from the electricity supply companies to power our equipment. The false idea is that we buy the energy, and it then gets used up in the equipment, so we have to buy some more to keep the equipment going. We accept it because that's what we were taught. It isn't true. The current flowing through the bulb can be arranged to be a charging current for another battery. It can both light the bulb and charge another battery without needing any extra current. Here, the circuit is powered by battery 1 as before, but this time the current goes on to charge battery 2. Yes, battery 1 gets discharged just as before, but the plus side is that battery 2 is getting charged up all the time. The final step is to swap the batteries over. And now, the newly charged battery 2 lights the bulb and charges up battery 1 again. Seem impossible? Well, it isn't. Nikola Tesla demonstrates this with his 4-battery switch system, where he chooses to use 4 identical batteries to implement this circuit. With 12-volt batteries as shown here, the bulb has the same 12 volts across it as it would have had with the single battery shown in the first diagram, as batteries 1 and 2 are wired in series to give 24 volts, while batteries 3 and 4 are wired in parallel to give 12 volts. The Tesla switch circuit swaps the batteries over with 1 and 2 taking the place of 3 and 4, hundreds of times per second. If you wire a simple manual changeover switch and use it to change the battery arrangement as shown above, tests show that the batteries can power the light for a longer time than if they were not switched over. The snag is that batteries are not 100% efficient, and so you can only take about half of the charging current back out of the battery again. For a Tesla 4-battery switch to operate indefinitely, there has to be inflow of outside energy to offset the poor efficiency of a lead-acid battery. NiCad batteries are more efficient, and so they are sometimes used in this circuit, where they can work well. There is another important factor involved in battery charging circuits to be used with normal lead-acid batteries, and that is the characteristics of the materials involved. The charging process in this switching circuit is carried out by electrons flowing down the connecting wire and into the battery. The electrons flowing along the outer surface of the wire move very rapidly indeed. The main current inside the battery is carried by the charged ions inside the lead plates inside the battery. These ions are hundreds of thousands of times heavier than the electrons. This doesn't matter at all once the ions get moving, but in the initial split second before the ions get going, the incoming electrons pile up like in a traffic jam tailback. This pile up of electrons pushes up the voltage on the terminal of the battery, well above the nominal battery voltage, and so the charging starts off with a high voltage, high current pulse into the battery. This is not normally noticed when using a standard mains-powered battery charger, as switch on only occurs once during the whole charging process. In the Tesla switch shown here, and in the Bedini circuits shown earlier, this is not the case. The circuit takes advantage of this difference in momentum between the electrons and the lead ions, and uses it repeatedly to great advantage. The technique is to use very short duration pulses all the time. If the pulses are short enough, the voltage and current drive into the receiving battery is far greater than a quick glance at the circuit would suggest. This is not magic, just common sense characteristics of the materials being used in this circuit. A person unfamiliar with these systems, seeing John Bedini's many advanced circuits for the first time, might get the impression that they are just crude, roughly built circuits. Nothing could be further from the truth. John often uses mechanical switching because it gives very sharp switch on and switch off times. John is a complete master of this circuitry and knows exactly what he is doing. The Electrodyne Corporation tested the Tesla 4-battery circuit over a period of 3 years. They found that at the end of that period, the batteries did not show any unusual deterioration. The batteries used were ordinary lead-acid batteries. The system operated lights, heaters, television sets, small motors and a 30-horsepower electric motor. If the batteries were run down to a low level and then the circuit switch on with a load, the recharging of the batteries took place in under 1 minute. No heating was experienced during this rapid charging. Heat was only produced during discharge cycles. They used mechanical switching and stated that below 100 Hz there was not much advantage with the circuit, and above 800 Hz it could be dangerous. They didn't mention why they consider that higher rates of switching could be dangerous. If we consider what exactly is happening, perhaps we can work out why they said that. The charging situation is like this. At time A the switch closes, connecting a voltage source, battery, charged capacitor, or whatever, to a lead-acid battery. Electrons start flowing down the outside of the connecting wire. Being very light and having little obstruction, they move very fast indeed. The electrons inside the wire only move a few inches per hour, as getting through the wire is difficult. All goes well until time B, when the leading electrons reach the lead plates inside the battery. Here, they have a problem, because the current flow through the plates is carried by lead ions. Lead ions are very good at carrying current, but it takes them a split second to get going due to their inertia. That split second is critical, and it opens the door to free energy. In that split second, the electrons pile up because they are still arriving down the wire at very high speed. So, at time C, they have built up into a large body of electrons. This large body of electrons has the same effect as if there had been a sudden connection to a much higher voltage source capable of supplying a much higher current. This situation only lasts for a very short time, but it has three very important effects. Firstly, at time D, it drives a much larger current into the battery than could reasonably expected from the original voltage source. Secondly, this high voltage pulse alters the zero-point energy field in which the circuit is located, causing extra energy to flow into the circuit from the outside environment. This is a bit like sunshine generating current flow in an electric solar panel, but instead of visible sunshine, the energy flow is not visible to us, and we have no instruments which react to this excess energy. Thirdly, the excess energy flows into the battery, charging it much more than would be expected, and at the same time, some of the excess energy flows into the load, powering it as well, and further, some of the flow goes back into the driving circuit, lowering its current draw. Remember Dave Lawton's water fuel cell? Well, Dave also connects a bulb across the cell to extract additional energy. A really interesting feature of this extra power draw-off is that when Dave adjusts the frequency to the optimum value, the supply voltage remains unchanged, but the input current drops noticeably and the brightness of the lamp increases markedly. Less input power at the same time as greater output power. The circuit hasn't changed, so from where is the extra power coming? One possibility is certainly that it is flowing in from the environment. So, returning to our excess energy is collected from the environment and used to both charge the battery and at the same time, perform useful work. The old saying, "you can't have your cake and eat it," just does not hold in this situation, as that is exactly what happens. Instead of the battery being run down from powering the load gets powered and the battery gets charged up at the same time. This is why, with this system, a discharged battery can be used to apparently run a motor. It works because the plates in the discharged battery are made of lead, which forms a bottleneck for the electron flow, causing the environment to charge the battery and run the load at the same time. That is why you get what looks like the magical effect of a discharged battery appearing to power a load. In passing, the more discharged the battery, the faster it charges as the environment adjusts automatically to the situation and feeds greater power into a flat battery. The environment has unlimited power available for use. John Bedini, who is expert in this field, has had motors running continuously for 3 or more years with the battery never running down and the motor doing useful work all the time. Great battery? No, great environment. Not necessarily exactly the same effect, but Joseph Newman's motor exhibits the same result, much to the discomfort of a conventionally taught scientist, who measured the motor at a minimum of 400% efficiency, really COP equal 4, and probably nearer 800% when all the major factors were taken into account. One thing which really bothered him was that when powering the motor on almost completely discharged dry cell batteries, the voltage measured at the motor was some 3 times the voltage at the batteries. That is very upsetting for a scientist who is not aware of the zero-point energy field and considers most systems to be closed systems, when in fact, there are practically no closed systems in our universe. Surprise, surprise, the Newman motor operates on electrical pulses. Anyway, returning to the Tesla 4 battery switch. For the vital buildup of excess electrons to take place, the switch closure has to be very sudden and very effective. A thyristor or an SCR might be suitable for this, but the sharp switching of a PCP116 opto-isolator driving an IRF540 FET is impressive, and a TC4420 FET driver could substitute for the opto-isolator if preferred. It is likely that the Tesla 4 battery switch circuit switching in the 100 Hz to 800 Hz region operates in this way. This drawing in of excess energy from the environment can be further enhanced by suddenly cutting off the electron flow from the original voltage source while the excess electron pile-up is still in place. This causes a sudden, very brief, further surge in the excess power, building up the voltage and current even further and increasing the battery charging and load powering drive. An even greater effect can be had if the next, short, sharp pulse is applied to the battery/load combination, just before the effect from the last pulse dies away. It may be that this is the situation which the Electrodyne Corporation people encountered when the pulse rate went over the 800 Hz rate. It may not be so much a case that the battery and load could not take the power, but more a case that the components which they were using were not rated high enough to carry that level of power. They do mention that if they went further, that they found that some of their circuit components started failing through not having high enough ratings. Notice that the output capacitors are rated at 100 volts, which is 8 times the nominal battery voltage. This was hardly a problem, considering that they had 12-volt batteries operating happily at 36 volts if they wanted that. They ended up building circuitry to hold the voltages down to a convenient level. To summarize the situation, the Tesla 4 battery switch appears to do the impossible through 1. Catching the current coming out of the load and using it to charge another battery instead of wasting it. 2. Providing very short, sharp, and rapid switching pulses which exploit the momentum of the lead ion's current flow. 3. Pulling extra energy in from the local environment to both charge the batteries and power the load at the same time. This leaves aside the possibility of 2 further gains available through very precise timing of the switching pulses, mainly to make the power available more easily and cheaply handled. So, it should be borne in mind that the practical issues involved in getting the circuit operating effectively are primarily about very fast, clean and well-timed switching. Multi-strand, very large diameter, high current rated wire will be helpful in getting the draw of excess energy into the circuit. Here is the switching sequence for the Tesla 4 battery switch system. As you can see, this is essentially the same circuit with batteries 1 and 2 swapping over with batteries 3 and 4. But he has added in 2 capacitors and a diode bridge of 4 diodes to power the load which needs to be inductive for the circuit, transformer, motor, etc. The circuit used by the Electrodyne Corp testers was. Please note very carefully that people familiar with conventional electronics will immediately say that the diodes in this circuit are the wrong way round. They aren't. This is not a conventional circuit. Firstly, the batteries need to be conditioned for using cold electricity, see Howard Haley's method in Chapter 6. Secondly, the 1N1183 diodes used here break down suddenly when reverse biased, and that pulse recharges conditioned batteries very quickly. This circuit was reported to have excellent results using 6 on/off switches on a motor-driven cam arrangement. Here 3 discs are mounted on the shaft of a motor as shown here. These are insulated from each other and the conducting sectors are aligned, and so are the brushes. The arrangement gives a mechanical switching such that when the upper brushes are short-circuited together, the lower brushes are open circuit. As there is a requirement for an inductive load for the circuit, the motor of a mechanical switching system could well form part of the load. Many people prefer solid-state switching to mechanical switching and so set out to design suitable circuits. It needs to be borne in mind that a very precise 50% mark/space ratio is essential and that may not be so easy to arrange. The common idea of using mechanical relays is not very practical. Firstly, relays have trouble switching at the speed suggested for this circuit. Secondly, with a contact life of say, 2 million and a switching speed of just 100 times per second, the relays would reach their projected lifespan after 2 weeks of operation, which is not a very practical option. To get an exact 50% mark/space ratio, possibly the following style of circuit could be used with a multi-turn preset resistor in position A. Here, the frequency is not noticeably affected by adjustment through a very wide range of mark/space settings. The output from pin 3 needs to drive a very sharp switching combination such as a TC4420 FET driver connected to IRF540 FETs. As the circuit diagram used by the Electrodyne Corp people is a little difficult to follow, perhaps the following diagrams may help by showing the current flow during the two states. Here, batteries 1 and 2 are wired across each other while batteries 3 and 4 are wired in series, in a daisy chain. This needs 3 on/off switches and the 2 diodes are inserted so that the plus terminal of battery 1 is not permanently connected to the plus terminal of battery 2, because in state 2, that connection must not be made. The state 2 wiring is almost identical, requiring another 3 on/off switches and 2 diodes to avoid a permanent link between the plus terminals of batteries 3 and 4. Here is a suggestion for doing that with PCP116 fast operating opto-isolators. Each of the 3 mechanical switches are replaced with a transistor, 1 PNP type and 2 NPN type. These need to be able to handle 30 amps, so although not shown here, they will probably be Darlington pairs with the low gain of the high power transistor being boosted by the additional gain of a driver transistor, perhaps something like a 2N3055/2N2222A combination. The transistor base current comes via a limiting resistor fed from an appropriate battery terminal affixed 12 volts above it. The switching is controlled via an opto-isolator and the 3 opto-isolators which switch together, shown above, are driven from one side of an astable multivibrator. The other 3 opto-isolators needed to perform the switching for state 2, will be off during state 1, so they will be driven by the inverted version of the same oscillator waveform. This ensures that 3 will be on and 3 will be off at the same time. The suggested transistor switching for the state 2 situation is shown above. This is just an attempt to perform the switching with the most simple components available, and has been shown to work in practice. The mechanical changeover switch can be replaced with transistors. The Electrodyne Corp experience indicates that it is likely that additional circuitry will be needed to cut off the extra power when the energy in the batteries rises to the point where it could endanger the equipment which it is powering or the components in the circuitry. The electronics tutorial which forms part of this ebook shows the principles which can be used for the design and construction of this kind of circuitry. It might be sensible to have the control circuitry kick in at 14 or 15 volts and drop out again when the battery voltage drops back to 12.5 volts or so. This switching circuit is said to be able to power its load indefinitely. It is also said that if one of the batteries is fully discharged, or nearly fully discharged, then putting it in any of the 4 positions returns it to full charge within 1 minute. The connecting wires should be at least 30 amp current carrying capacity and the individual diodes and the diode bridge are rated at 35 amps 50 volts. The circuit is intended for use with lead/acid batteries, but it has been used successfully with rechargeable nickel-cadmium batteries. The circuit provides about 12 volts as the output, so mains equipment would be operated using a standard, commercial inverter which converts this low DC voltage to normal mains AC voltage capable of powering TV sets, DVD recorders, or whatever. There have been various different versions of the Tesla 4 battery switch circuit. Some of these show additional diodes, making an absolutely symmetrical circuit where the current flow can continue even if the load is disconnected, as shown here. I have been asked to explain how the switching might be achieved. Usually there are many different ways to achieve any wanted effect and switching circuits are no exception. What follows then is just a suggestion for one possible way of doing the switching and must not be thought of as the way in which the switching must be done. The main objectives for the switching circuit are to have very fast switching and to have an exactly equal on period for the 2 switched states. As electronic components have manufacturing tolerances, it is not possible to have components with exactly the same values unless they are selected from a large stock of the same component. To deal with this situation, and avoid spending large amounts by buying high specification components, we will aim for a manually adjusted circuit, where the switch on time can be adjusted to give exactly the right value. This circuit allows the mark space ratio to be adjusted without altering the frequency, and the frequency can be adjusted without affecting the mark space setting in any way. In the Tesla switch circuit, 3 switches need to be in their on position and the other 3 switches in their off position, so we will arrange this by using the ordinary NE555 timer circuit shown above, with its adjustable mark space ratio, that is, variable on-to-off ratio. We will use this circuit to drive 6 opto-isolators which will turn the 6 transistors on and off in groups of 3 as required. To get the very high switching speed needed, PCP116 opto-isolators should be used, and although these are difficult to find, every effort should be made to get them as they enhance the switching speed. One feature of the Tesla switch is the fact that it should have an inductive load. In simple terms, that means that the load should be a motor or a transformer. The need for an inductive load may well be the back EMF voltages which are developed when the current flowing through the load is cut off suddenly. So, let's start with the circuit shown below, which has a transformer as the load. In this circuit, switches 1, 2 and 3 switch on and off at the same time, and switches 4, 5 and 6 form the second group. If one group of 3 switches is on, then the second group of switches needs to be off. The following details show the preliminary stages of an implementation using 4N25 opto-isolators, which are not nearly as satisfactory as PCP116 chips, which switch typically 30 times faster. However, the circuit adaptation is very minor in that it is only one board which needs to be altered. The circuitry choice was as follows. Here, each of the 3 mechanical switches are replaced with a transistor, 2 NPN type and 1 PNP type. As these were required to be able to handle 30 amps, the initial build used the Darlington pair devices MJ110164. The NPNs and MJ11015 for the PNPs, as these are rated at 30 amps and have a minimum gain of 1000, allowing quite low switching currents for the control circuitry. The switching is controlled via an opto-isolator, and the 3 opto-isolators which switch together as shown in the diagram above, are driven by the output of a 555 timer chip astable multivibrator. Chapter 12 explains all of this, so if you are not familiar with these things, then perhaps it would be a good idea to read through that chapter now. The other 3 opto-isolators needed to perform the switching for state 2, will be off during state 1, so they will be driven by the inverted version of the same 555 signal. This ensures that 3 will be on and 3 will be off at any time. We need to get an inverted output from the timer circuit, that is, an output which goes high when the 555 timer chip goes low and which goes low when the 555 timer chip output goes high. There are various ways to do this, but the way shown here is the very simple method of using a transistor. If we were using mechanical switching, we would choose to use a switch which opens one set of contacts before closing the other set. We can arrange that by making the switch on of the inverting transistor adjustable, like this. The 5K variable or preset resistor is placed across the output of the NE555 timer chip. This resistor will have either a very low voltage across it or a voltage nearly the same as the battery supply. Please remember that the 555 chip can't handle supply voltages over 15 volts and will burn out if you feed them anything more than that. The Tesla switch circuit with 12 volts batteries should be okay, as you don't want the batteries to exceed 14 volts anyway. When the 5K variable resistor has a high voltage on it, every voltage from 0 to that high voltage can be selected by moving the slider of the resistor along its track. At some point when the slider is gradually moved up from the minimum voltage point, the transistor will turn on. The 3K resistor limits the current if the slider is moved to the very highest voltage point. The output transistor can be a BC109 or a 2N2222 type, as these are high-gain types easily capable of handling the tiny current needed to drive 3 opto-isolators. The variable resistors come in a wide range of types. It is probably best to use a preset type, as they are very easy to adjust and hold their settings very solidly. Also, when the correct setting is found, the component will be left on that position permanently. Some common types are where some can be adjusted from the top and others adjusted from the side. All of TGM can be mounted directly on the strip board or printed circuit board used to construct the circuit. The initial build can be done in simple stages. This is to ensure that the switch wiring is correct before the semiconductor switching is attempted. Although the circuit does not show it, it would be no harm to have a fuse on each battery, as a battery holds a considerable store of electrical energy and is easily capable of starting a fire if there is an inadvertent short circuit. The excessive current draw caused by a short circuit is not visible, and the first you know of it with a battery-powered circuit is the burning smell and wisp of smoke. Even using a mains-powered power supply unit with voltage and current displays, it is still very easy indeed to miss a short circuit, as you tend not to be watching the current display when the problem occurs. To make the assembly and subsequent adjustment simple, a standard strip of ordinary screw connectors is used. For initial testing, a 4-pole 3-way wafer switch is used. The switch provides the two changeover switches and the single on switch and the single off switch. It also has the advantage that the third switch position switches the entire circuit off. The initial test uses a low current load of 2 LEDs with limiting resistors wired in opposite directions. This shows the direction of current flow and confirms that the switching is working correctly. By omitting the capacitors and pulse switching, it allows leisurely checking of the wiring and operation. The physical layout with a mechanical rotary 4-pole 2-way switch could be. And the diodes used here happen to be high-speed, IXYS type DSEI12, 10A, which were to hand and which are rated at 1000 volts, 12 amps. While this does limit the initial current capacity, there is no reason why these cannot be doubled up or tripled up to allow a higher current. The batteries used initially in the test are very small 1.2 AHR types, and so the allowable current draw from them is quite limited. If this circuit does not operate correctly straight off, it is quite likely that the diodes are the wrong way round. In this physical layout, the back of the diodes all face upwards. This particular build looks like this. State 1 with the right hand LED lit. State 2 with the left hand LED lit. So far, this shows that the batteries, diodes and switch connections are correct. The next step is to change the switching for one of the states to transistor switching. This requires 3 transistors, 3 optoisolators and 3 resistors. The transistors are housed in the large 2-3 package and so will mount on the baseboard. The small components can be mounted on a standard small piece of strip board, 10 strips with 38 holes per strip. There should be a voltage drop of at least 10 volts, 11.5 volts to 1.5 volts, across the resistor feeding the base of the transistors. If the transistor current is 10 amps and the gain 1000, then 10 milliamps will be needed as the current into the base, so with a 10-volt drop the resistor should have a value of 1K. The current through the LED section of the optoisolators is limited by a 330 ohm resistor, which can be positioned anywhere convenient in the chain as the same current passes through all of the LEDs inside the optoisolators. The circuit diagram for each set of 3 optoisolators could be. The first part of the circuit is now wired up to switch when the first chain of 3 optoisolators is powered up to feed base current to the 3 power transistors. When this section is working correctly, then the board containing the first chain of 3 optoisolators is extended to hold an identical additional chain of 3 optoisolators as shown here. You will notice that for convenience, the physical layout is arranged so that the strip board is just rotated through 180 degrees and the wiring diagram for the first 3 optos is used again for the second 3. The underside of the board looks like this when turned over from left to right. And with the power transistors wired in place and ready to receive the optoisolator connections. The 2 chains of optoisolators now do the actual switching when they are powered up in turn. This spread out simple layout makes testing and checking easy and no heat sinks are needed for low current testing. So with the optoisolators wired in place, the switching is solid state. Here, when one of the brown wires, seen at the bottom left-hand side of the picture, are touched to the minus terminal of battery 2, one LED lights up. Disconnecting the wire and touching with the minus terminal of battery 2 with the other wire, lights the other LED. Obviously, you don't connect both of the wires at the same time. It would be sensible to have a fuse on the positive lead coming from each of the batteries, as this protects against accidental short circuits and against the failure of any of the main power semiconductors. In the picture above, most of the wires coming from the opto board appear to be connected via the lower terminal block. This is not the case, as only the 6 leads coming from the base connections of the power transistors actually use the terminal block, while the other wires are just routed through the block as being the most direct way of reaching their connection points further in on the board. It should be stressed that the opto-isolator connections are not random. These are not mechanical switches where it doesn't matter which way round the switch is connected. The optos are transistor junctions, and the connections to the PNP transistors in the middle of the board are made the opposite way round to that for the NPN transistors. In other words, pin 5 goes to the base of a PNP transistor so that it gets switched through to the negative side of the battery powering it, while pin 4 goes to the base of an NPN as it needs to be connected to the positive side of the battery powering it. As well as paying attention to which wires go to the bases of the 6 transistors, it should be noted that if you wish, instead of having 2 wires running from the board to the positive supply for the board, that an alternative is to make the positive line connection for the second chain of opto-isolators physically on the board, as both chains are fed from the same voltage source, which for the moment, is battery 2. When this stage is working correctly, the manual powering of the opto chains is replaced with a solid-state switching board to allow high-speed, reliable switching. There are various options for the design of this switching circuit. The initial design opts for simplicity and hopes that the opto-isolator switch on and switch off rates will be fast enough to make the overall circuit operate as desired, pulling excess energy from the local environment in spite of using 4N25 opto-isolators. This may look a little strange with the collector of the output transistor not appearing to be connected to anything, but it connects to one of the chains of 3 opto-isolators with its built-in current limiting series resistor. The normal pin 3 output from the NE555 chip connects directly to the other opto-isolator chain, so one will be switched off and the other one switched on at the same time. The timing resistor can be varied from 3.3 kΩ to 50.3 kΩ, and that combines with the 220 nanofarad capacitor to give switching in the required frequency range. And the underside of the board when turned over from left to right, is tuning of the mark space preset resistor is initially set to its center position, and if the batteries start to develop different voltages, then it is adjusted slightly and running continued, aiming for exactly the same voltage on each battery. The batteries should be the same age and the same ampere-hour capacity. George Nikoli, A Detailed Study of Stephen Mark's TPU. Here are some observations by George Nikoli, who says, "This study will bring us closer to understanding the toroid of Stephen Mark, but not all the way to total understanding. I have discovered the real construction behind the TPU from hours and hours of frame-by-frame carefully and methodically watching small videos. First, I have come to believe that the various TPU-like devices presented by Stephen in his videos, are very different from each other. That is why there are so many different configurations, building plans, variants, opinions, topologies and implementations of Stephen's TPU. The term TPU, meaning toroidal power unit, is inappropriate, because the principle of operation has nothing to do with the toroidal shape. Stephen Mark has chosen just to implement the principle inside toroidal cores in order to capture most of the magnetic flux. The simplest and most transparent of Stephen's devices is this one, the one that can be studied in detail. So let's decide on a convention for naming the parts which we see in the device. Many people say that Stephen's TPU has 3 coils inside it. Let's take a closer look. We can first note that there appears to be 4 segments, and therefore, there must be 4 coils. Pretty obvious, this one. Same here. This one is obvious too. The 4th coil is a little difficult to see. Yep. It's there all right. Here is another view. Okay. Let's summarize what we have seen so far. We seem to have some kind of a transformer with 4 coil windings, and this one doesn't resemble in any way the common conceptions of Stevens TPU construction. These are nowhere near the configuration which we are studying here. These configurations seem absurd to me. Where the heck do we ever see this type of arrangement in Stephen Mark presentations? I haven't seen this anywhere. But hey, maybe the guys who say these things know better. I only know what I see. The rest is speculation. Although in some cases educated guesses are acceptable. Okay. What do we know so far? Some say that this 4-coil Stephen Mark toroid-like transformer is similar to Tesla patent 381970 system of electrical distribution. Interesting, looks similar. Let's take a closer look. Okay, anyone who takes a look at this might get confused by all these wires. Let's analyze what we have here, because it will help us a lot in figuring out how Stevens TPU works. How does this work? Let us look at the generator. Let's quote Tesla. It will be observed that at a given point of time the coil G is in its neutral position and is generating little or no current, while the other coil, G, is in a position where it exerts its maximum effect. US Patent 381970 page 2, line 95. So this generator has 2 coils perpendicular one to the other inside a simple NS magnetic field, 2 poles. The commutator has 4 contacts, from the 2 starts and 2 ends of the 2 coils, and there are 4 wires coming out of this generator. Simple stuff. As the generator spins, it outputs the waveforms in the right. Just a 2-phase electric generator typical of Tesla, nothing fancy here. Okay, so 2 signals 90 degrees out of phase from each other, going into the transformer. One signal is a sine and the other a cosine. So what happens? Then, let's look at the transformer. Let's simplify a little bit and take this Tesla transformer apart. This is the basic configuration, so we have 8 coils here, and not 4, like in the TPU. This is important. This is the easiest place to start to understand how the TPU works. Okay, let's continue with harder stuff. So, the TPU has 4 windings, or does it have 8? Let's take a closer look. Not very clear, so let's look further. Wow, what do we have there? It looks like 2 big thick heavy wire. Could it be? Could it be a bifilar coil? It's definitely a bifilar coil. Here we can see that it is too thick to be only 1 wire. There must be 2. Look closer and really pay attention. Each of the coils have 7 turns and they are definitely bifilar coils. There will be no point in having just the left coils bifilar, and the rest simple coils. It's got to be that all are bifilar. It's the only way to make sense. It's got to be a balanced symmetrical system. It's an educated guess. I hope you agree. If you don't agree, then find a better quality video, take a closer look than I did, and prove me wrong. So let's summarize what we do know so far. This is Tesla technology. We need to study Tesla's patent number 381970 in the most minute detail. So, let's see how Tesla's transformer works. What is really interesting in this configuration is the way in which these coils are connected to each other. If we look closely, then we notice that they are connected in opposition to each other. So the magnetic flux created by these coils is cancelling out. Weird. How can a transformer work in such a way? Well, your understanding of this depends on your expectation of how it must work. It will work, but the efficiency will be very, very poor. But Tesla knew all of these things and more, so then he must have been looking for something else he was exploiting and investigating an effect. The magnetic flux vectors from these coils in operation looks like this. And the firing stages of the Tesla transformer are A slightly more accurate representation of the magnetic field lines at one stage is. Now what happens is, that when you energize two opposite coils like this, you will get output power on their matching secondary coils. If you build a transformer like this, and short-circuit the secondary, see what happens. What do you think will happen? Well, conventional education tells us that we will see a spark, and if we continue with the short circuit, we could overheat and destroy the secondary winding. But not in this transformer. This type is a so-called lensless solid-state generator. Meaning that no matter what you do to the secondary winding, you will not affect the primary winding in any way. No matter how much power you extract from the secondary, the primary will never see it. It will not see a load connected to it. And even better, when you connect a load to the secondary, the input power decreases. Quite the reverse of what you would expect. However, don't get your hopes up, because this is only half of the story. Here is the other disappointing half. Even though this might seem like a huge cop, we are forgetting to take account of the power which the transformer itself consumes, even when no load is connected to the secondary. This is interesting stuff, but in Stephen Mark's TPU we have this lensless opposing magnetic flux/magnetic decoupling effect in the coils as seen in the Tesla patent. All of the 8 coils of Stephen's TPU appear to be wired in series, one after the other in a chain. Let's take a closer look. Okay, so the front left coil starts from below and is wound clockwise, viewed from the front. This leads us to the logical deduction that its end will exit the coil from the upper side of the coil. Now, look at the back left coil. The back left coil is wound in the same clockwise direction, if you start the windings of the toroid in a clockwise direction when viewed from above. Let's continue to investigate this. This is very difficult to see, but he has changed the direction of the winding to counterclockwise, if you consider the start to be where the wires come out of the device. The front right-hand coil is wound in a counterclockwise direction. It starts from above, and ends below. Now we know all the directions of the windings with a high degree of certainty. Let us summarize what we know so far. As suspected, Stephen is creating the effect we are after, by using opposing magnetic fluxes. Let us take a look at that bundle of wires in the middle of the TPU. Where do they connect to? This is the toughest job, but we can clearly distinguish 2 wires connected to, or coming from, the right pole. How are these wires connected? To what? What other wires do we have here? We could combine them like this. This would be foolish, because the front left-hand coil would be rendered useless. Another combination could be. This would be ineffective also, because this time, the back left coil will be redundant. Other combinations could be like this. In these configurations, we have 2 sub-possibilities, both ineffective, as we will see. The first sub-possibility is that the current flow through these 2 yellow wires is in opposite directions with one going and one coming. Regardless of which one's which, let's think also about how the front left coil enters into this junction, and how the back left coil leaves this junction. If the wires were connected like this, it would nullify our pole. So then what's the point in having the permanent magnet placed here? Our coils don't create a magnetic pole here. So, this sub-possibility has to be wrong. The last incorrect sub-possibility is that the direction of the current flow through these 2 yellow wires is in the same direction. If the wires are connected like this, then you might say, what's the point in having 2 wires with the same current? It can be just one and you are right. If so, then it's a median point. But what if it's not the same current? It could be 2 sequential pulsed currents, when one is on, the other is off and vice versa. If the wires are connected like this, then bear with me, because it gets a little complicated. To pulse 2 flip-flop currents through these 2 yellow wires, will mean that you will need a ground for them. The only possible symmetrical ground for them will be on blue wire in the right pole. Now, this is somehow peculiar, but the blue 4 coils, let them be primary coils, will generate 4 magnetic poles like so. But this configuration has also to be wrong. Why? We will considering the blue coils to be our primary, then the red coils will be our secondary. Our primary fires first the back side of the TPU, then the front side of the TPU, and so on. By doing this, our secondary, due to not having any sort of connection at the back pole, will generate 2 equal voltages of same polarity at the A and B terminals. Due to the fact they have the same polarity at a particular time, either plus or, an equal voltage, there will be no voltage drop between them. The only way to collect power from this type of red secondary is to have a ground connection at the back pole, because our voltage potential is created from this point. But we cannot see any wire connected to the back pole. Therefore there is no possible way to generate an output from this red secondary configuration. The only remaining most likely possible configuration will be like this. This is straightforward. First we have reached the point where we can say with certainty that Stephen is using a tapped median point on the left pole, therefore, regardless of the direction of the current in or out of these median points, he will have created 4 magnetic poles, at the front, back, left and right of the TPU. How are the poles really oriented? How are the magnets oriented? How is he firing the coils? Let's study possible answers to these questions. Stephen says that his devices produces only DC. That to me seems pretty logical. Why? Well, because of the magnets which he places on the top slots of the TPU. He is using 2 magnets, one on the right-hand pole and one on the left-hand pole, conventional naming from the camera point of view, and from the wires that come out of the TPU. If you are going to use permanent magnets, oriented like this, with either south or north pole upwards or downwards, you must excite these coils only with pulse direct current. It's the only way it will work. Pulse direct current is the only logical way. So then, we definitely know he is pulsing the coils with DC, but how? Well, here my research stumbled a bit. The most likely configurations are as follows. This would imply that we start from the left pole as the positive lead, but we will end up with 2 separate ground connections which must be connected together and form one ground. Therefore our final, and only possibility will look like this. This could be one very possible configuration for a working model, but it still has a long way to go. I intentionally did not mention an obvious construction detail until now, indicating the reason why he built it in the way that he did. If you haven't yet figured it out by now, let's think about this topology for a second. We know from the Tesla transformer that it is extremely inefficient due to the fact that more than 80% of the field created by the primary coils is situated outside of the core, and can't be tapped, although there are some implementations which use a rotor, inside the Tesla transformer. So how can we close all the magnetic field lines, to increase its efficiency? That is the correct and right question. The answer was found by Stephen Mark with his clever and ingenious design. You probably think that I've made a mistake and that the front pole in fact has no core. That's true, there is a junction box there, but again, you get the picture. You might think that the top core disc is just for design. If so, then you are so wrong. It's actually what makes this design unique. It's what makes it work. It's the key to magnetic containment. It's how Stephen Mark figured out how to return the opposing magnetic flux lines in the Tesla transformer through another one on top. The top disk provides the return path for the opposing magnetic fields created by the coils. You might think that the top core disk is just for design. If so, then you are so wrong. It's actually what makes this design unique. It's what makes it work. It's the key to magnetic containment. It's how Stephen Mark figured out how to return the opposing magnetic flux lines in the Tesla transformer through another one on top. The top disk provides the return path for the opposing magnetic fields created by the coils. With this configuration we can proudly say, outside magnetic field? In theory, 0. Efficiency? In theory, 100% energy conversion. So let's theorize a little bit now. If this configuration can have a core with a high permeability, then a primary winding and a secondary winding that generate such a field, 4 closed magnetic circuits, would have in theory above 98% efficiency. You might say that's ridiculous high and I'm forgetting about iron losses. No, I'm not. Regarding this, iron losses are energy losses due to hysteresis, magnetization and demagnetization of a ferrous metal. Right, but you have to remember that we are only working in the first quadrant of the hysteresis cycle. That means that we are not demagnetizing the core. The core is in fact reaching magnetic saturation. It is always magnetized in one direction. That is another reason why we must place the magnets carefully, always in one way. We shouldn't reverse them during experiments, because due to the high magnetic flux density, the retentivity of the core will be at a high state. So if we change the direction, we have to spend extra energy to reset, reverse it, that is in theory anyway. Now here's another theory: what if we can provide an already existing magnetic field, in the same configuration and direction as the flux generated by the coils, so that we can raise above 100% efficiency? Wouldn't that be something? I have come to believe that the reason Stephen Mark is using permanent magnets might be the same thing as Charles Flynn does in his solid-state electric generator. This is another transformer, but which has a magnet in the middle. What's the point? The point is to manipulate the opposing flux fields generated by the coils with these magnets, to reinforce the field created by them, and to spend a little less energy in creating a magnetic field once you have one already from the permanent magnet. The Charles Flynn generator works in a different manner, but Stephen Mark's TPU is using magnets for the same reason. If one of the TPU magnets has its north pole facing upwards and the other magnet has its south pole facing upwards, then the magnetic field created by them will bypass the front and back magnetic poles of the TPU. There will be just these two poles created by the magnets, two magnetic closed circuits. This configuration must be wrong, because of the direction of the magnetic field from the magnets with this arrangement. Half of the magnetic field would opposite the magnetic field created by the coils. Remember how those fields are orientated. The coils change their winding direction at the front and back pole, so we have two magnetic fields in opposition in these places, and one of them will be also oppose the field from the magnet. But by using them in repulsive mode, and orienting them so that they both have similar poles facing in the same direction, then their fields will look exactly like the ones generated by the coils. So now, we have determined with a high degree of certainty how he orients his magnets in the TPU. This is where this deductive, and certain study ends, but it's not over. If, like me, you feel drawn to this type of technology, then please continue the work which I have started here. I am going to continue further, but from this point on, please be aware that I am going to guess a lot, so the certainty factor will be greatly reduced. Firing the coils. How is Stephen exciting the coils? Well, we do know for a fact that he is using pulsed DC, but how is he driving this type of pulsed current through the coils? Which connection points does he use? It seems most likely that he is using a square wave with sharp rising and falling edges, the so-called kicks. Some say that he isn't using any type of control circuit board, and no integrated circuits. That seems most likely to me, because Stephen says that his device is extremely simple. So let's keep things as simple as possible. I'm not saying that having IC control board for a TPU is complicated. I think that there are no MOSFET in his device. Why? Well, think about it. If he were to use MOSFETs, then they would have to switch at least 100 volts at more than 10 amps, judging by the wire gauge which he is using. He would also need a control circuit to drive the gates of these MOSFET, and due to the closed feedback loop, and having no battery in the device, he would have to generate a low voltage and low current inside a some sort of feedback/coil that drives the gates in order not to burn those transistors out. But nothing which we have seen supports that. Therefore the supposition, that he is not using MOSFET transistors, is likely to be true. I'm not saying that with a high degree of certainty, as I could be wrong. There is no feedback coil in this system, and that, I state as a fact. This system is balanced and symmetrical, and we have chosen for the sake of conventional knowledge of transformers, terms like primary windings and secondary windings. But we know that we are dealing with a 1:1 ratio transformer, therefore the primary can be used as a secondary, and vice versa. You could swap them, because they are identical. That's a fact. We also know that this transformer has a median point in its secondary, and also his primary winding has a median point. 2 median points in his transformer, at the left pole in the pictures. I believe that he is somehow using a common bistable/astable bipolar transistor circuit, with only 2 transistors. Why do I think that way, and could it be that simple? I believe so. I think he is using a flip-flop circuit to drive these coils. So in this arrangement the TPU should work like this. This configuration is most like to be to operation of the TPU, because now it is very similar in operation to the Charles Flynn generator. It has a simple working principle. When you understand how the Flynn generator works, then you will see that Stevens TPU is actually a better version of the same technology. Although this type of generator is working in AC, Stevens TPU can't work like that due to the coil winding direction at the front and back poles. Check the picture above, and you will realize that if you change the direction of the current through the TPU coils, then the 4 magnetic poles created around it will alternate and the magnet will vibrate, because one moment it is attracted by the flux inside the TPU, and the next moment it is repelled, so it can't work with sine wave AC. By implementing the Charles Flynn solid-state generator in a toroid core, it becomes more efficient, due to providing a better magnetic flux containment construction. This is the end of this research. Don't take everything which I said to be fact written in stone, but instead, judge for yourself. If you find these things presented here useful, fine, I'm glad that it helped someone.